welcome you all to the lecture number 3 of week 2. In the last lecture, that is lecture 2 of week 2, we started our discussion with the universal gates, that is the NAND and NOR gates, followed by the bubbled input AND and OR gates. Our discussion then moved on to the Boolean function and expressing the function as SOP, that is standard sum of product, and POS, that is product of sum, using the truth table and Boolean laws and its realization using two-level logic gates. Today we will begin our lecture session by solving one of the questions of practice problem 2 of week 2, and from there our discussion will move on to minimization of Boolean function using Boolean laws and Carnot's map. One question: the number of NOR gates required to obtain AND operation. So we know that a two-input AND gate having two input variables A and B, the output F will be A dot B with the dot operators, A and B with dot as the AND operator. Now we have to implement this AND operation using NOR gates. Fine. So we have got three NOR gates where the two input variables are A and B, and we have got three NOR gates, two input NOR gates. So you can see that the first NOR gate where the input variable A is given, there the two input NOR gate is made as 1, and similarly for the input variable B, the two input NOR gate is made as 1. So the output of the NOR gate for the input variable A will be A bar, that is A plus A, that is A with the inversion, that is A bar. Similarly B plus B with the inversion, that is B bar, and this is fed to the third as input to the third NOR gate, and that will be A bar plus B bar with the inversion, because there is a bubble at the output, that is the NOR gate. So A bar plus B bar, the whole bar. Using the De Morgan's theorem, you know that A bar plus B bar, the whole bar, can be written as A double bar dot B double bar, where, or A double prime dot B double prime. So A complement of A, the double complement of A is the A itself. Similarly, the double complement of B is B itself. Therefore, we will get as A dot B. Therefore, for implementation of an AND gate using NOR gates, we require three NOR gates. Now, you have one more question. Draw the output waveform of a two-input AND OR gate whose inputs are square waveform of 1 kilohertz and 2 kilohertz respectively. The question says that there are two input variables. One input variable is a square wave with frequency of 1 kilohertz. The other input variable, let we call it as B, with the frequency of 2 kilohertz. They are fed to two gates. One is an AND gate and OR gate. Now we will see the result. So this is a square waveform. You can see that the first the figure is a square waveform of 1 kilohertz. We can have got each division is of 0.25. You can say that for 0.25 millisecond. So you can see that for 0.5 millisecond it is on the waveform, and for again 0.5 millisecond the output is 0. That means logic 1 and logic 0. Similarly, if you see waveform B, which is of 2 kilohertz, we can see that its frequency is 2 kilohertz. Therefore, 1 by 2 kilohertz, that is of 5 milliseconds. So you can see that 0.25 millisecond the waveform B has an output as logic 1, and the another 0.25 second it has got a logic output which is equal to 0. So first we will go for the OR operation, that is A plus B. You can have divided into 4 time divisions, T1, T2, T3 and T4. So you can see that within the time division T1, you can see that both the outputs of waveform A and B are at logic 1. Therefore, the output will be, because A plus B, 1 plus 1 is equal to 1. Then from T1 to T2, we can see that the waveform A has logic 1 and the waveform B has logic 0. Again, we are going for the operation OR. 1 plus 0 is again 1. Then we have got from T2 to T3, we have got the waveform A, the output of which is at logic 0, but of waveform B it is at logic 1. Therefore, 0 plus 1 is again equal to 1. And from T3 to T4, you can see that both the waveforms, that is waveform A has got the output logic 0. Similarly, the waveform B has got the output logic 0. therefore 0 plus 0, therefore the output will be 0. So you can see that the waveform of A, you can see that from 0 to T3 the output is high, and from T3 to T4 the output is low. The same waveform, that is waveform A and B, is now fed to an AND gate. So you can see that from 0 to T1, when both the output of waveform A and B are 1.1, the output will be 1, and from T1 to T2, the waveform A has got logic 1, but that of B is logic 0, therefore 1.0 is again 0. Similarly, from T2 to T3, you can see that the output of waveform A is 0, but of waveform B is 1, so 0.1 is again 0. And similarly, you can see that from T3 to T4, you can see that both the output of waveform A and waveform B are 0, so 0.0 is 0. So you can see that if I say the duty cycle is more for an OR operation. That means the time period for which the output is 1 is more for an OR gate, and for an AND gate you can see that only from 0 to T1 the output of the AND gate is at logic 1, remaining from T1 to T4 the output of the AND gate is at logic 0. Implement the exclusive OR gate with input variables A, B and C. So you have got 3 input variables. I have used one exclusive OR gate. The first exclusive OR gate have got 2 input variables, that is A and B, the exclusive OR operation of which is A exclusive OR B, which acts as an input to the second exclusive OR gate with C as the other input variable. So we finally get the output as A exclusive OR B within bracket exclusive OR C. So we have performed the exclusive OR operation truth table with 3 inputs, that is A, B and C. So when we make the truth table, if the number of input variables are 3, then the possible number of combinations is 2 raised to 3. That means there are 8 possible combinations. So you can see the last column, which is denoted as Z, you can see that when all the inputs are 0, the output is 0. When one of the input is 1, you can see that the third row, where A is 0, B is 0 and C is 1, you get as the output 1. And when you can see, you come to the fourth, that is when A is 0, B is 1 and C is 1, the output is 0. That means, and you come to the last row, when all the 3 inputs are 1, when A is 1, B is 1, C is equal to 1, the output is again 1. You can see that when all the inputs are even, the output is 0, and where having even number of ones, the output will be 0, and when all the inputs having odd number of ones, that is when you can see that when A is 1, B is 1 and C is 1, the output will be 1. So therefore, you can use your exclusive OR gate as an odd parity generator for parity error correction and detecting codes. So what we can conclude is that if the number of ones in the input variable is even, the output will be logic 0, and if odd, the output will be logic high. And we can also say that the exclusive OR gate follows both commutative and associative law. Now we will come to the next topic, that is minimization of Boolean function. The realization of standard sum of product or product of some Boolean function using logic gates depends on, first, the number of variables in the function and the number of mean terms and max terms. If it is sum of product, it is the mean terms, and if it is product of sum, it is the max terms. The number of inputs to a gate at level 1 depends on the number of variables, whether in normal or its complement form. So therefore, the realization of SOP or POS depends basically on the 2 conditions. First is that the number of variables in the function and the number of mean terms and max terms, and the number of inputs which are required for the gate at level 1, and that again too depends upon the number of variables, whether this variable is in its normal form or in its complement form. The question comes, why we require minimization of Boolean function? The answer for which is to reduce the cost of circuitry, to reduce the cost of complexity, to improve the stability, because as the number of gates gets reduced, the number of ICs required for implementation of the logic function that gets reduced, the size of the circuit and the interconnections which is required for connecting the variables from one gate to the another gate, that also gets reduced. And when you have lesser number of gates, the power dissipation also gets reduced, the footprint also gets reduced, that means the size also reduces, and the stability of the overall circuit also improves. The number of variables in an Boolean expression can be reduced by, what are the two methods? Algebraic manipulation of the given function using Boolean laws, or how we can reduce a Boolean expression. The first point which comes into mind is use of algebraic manipulation using Boolean laws, but the main drawback of this algebraic manipulation is that there are no set rules to be followed so as to guarantee that the final result which you obtain is in the minimized form. So, we will take an example. Reduce the following Boolean expression to a minimum number of variables. So, we have got a function f which is given as f is equal to a bar b dot within brackets d bar plus c bar d bracket close plus b dot again within bracket a plus a bar a c d. You can see that this function f has got 4 variables a, b, c and d, whether in its normal form or in its complement form. Therefore, how to reduce it using algebraic manipulation and using the Boolean laws. So, what we can do is that we can now use the distributive law. So, we can write this expression as a bar b d bar plus a bar b c bar d plus a b plus a bar b c d. Now, we will come to step number 3. Combine the terms of the function with common variables as a bar b dot d bar. You combine the term 2 and 4 like this: a bar dot b dot d dot within bracket c plus c bar plus a dot b. So, you know that applying Boolean laws, that is the OR law, c plus c bar is equal to 1. So, therefore, the function further gets reduced as a bar b d bar plus a bar b d. So, here also what we can do is that you can combine the terms, the common terms. So, it will become a bar dot b dot d plus d bar. Again we know that through OR's law d plus d bar is equal to 1. The function finally becomes a bar b plus a dot b. Further reduction gives you take b as the common variable among the two mean terms and you get as b dot a bar plus a, and we know that from the OR law a plus a bar is equal to 1. The final Boolean function f after minimization, you get f is equal to b. So, what you have seen is that when you started going for the Boolean minimization, we have got 4 input variables. These input variables may be the sensor outputs. Suppose if I am an electrical engineer, we have got 4 output from 4 sensors. One may be the current, the other may be the voltage, the third may be the speed, and the fourth may be the temperature. And finally, we see that the logical function of the Boolean expression got reduced to a single input variable and it can be realized as f is equal to b. Now, we come to another example. F is equal to within bracket and within bracket a dot ab bar dot c bracket close dot a dot b bar, the bracket close, the whole within bracket plus bc, and again the full bracket, the whole with a prime, that is a complement is there. So, now we can apply the De Morgan's theorem. To apply De Morgan's theorem, you know that a plus b bar is equal to a bar dot b bar. So, where the term a is, you can say that my term a is a bar c, a b bar c the whole bar plus a dot b bar the whole bar dot bc the whole bar, you can write it as b bar plus c bar. Now, the first term again you can simplify it using the De Morgan's theorem, where we have written as it is equal to a b bar dot c the whole bar, it can be written as a bar plus b double bar plus c bar plus a bar plus b, again I have applied De Morgan's theorem, dot b bar plus c bar. So, now you can apply AND laws to the second and third term. So second and third term, I just use the distributive property and we have applied the AND laws. You can say that A bar plus B double bar becomes B plus C bar within brackets dot A bar B bar plus A bar C bar plus B dot B bar plus BC bar. So we know from the AND law B dot B bar is equal to 0. Therefore, that term gets reduced. The final we have got F is equal to A bar plus B plus C bar within bracket close dot, again starting with bracket, A bar B plus A bar C bar plus BC bar. And again you can see that you use the distributive property and apply the AND law. So we can see that we can write this as A bar B plus A bar C bar plus A bar BC plus A bar BC bar plus BC bar plus AB bar C plus A bar C bar plus BC bar. In step 5, what we will do is that we see that if there are two terms which are getting replicated, fine, which are appearing twice in the function. If it is x, if it is there, then you can remove them, one of them. So we know that A plus A is equal to A. So finally we will get an expression F is equal to A bar B plus A bar C bar plus A bar BC bar plus BC bar plus A bar B bar C bar. So again you can see that you can make some common terms and remove any other input literal or variables. So we can see that A bar B bar plus A bar C bar plus A bar C within brackets B plus B bar. That is, the common term is A bar C and within the bracket B plus B bar. That means you can see that what I have done is that I combined the third term and the fifth term plus BC bar. So you know that B plus B bar, that is as per the Orr's law, it is equal to 1. So therefore it becomes A bar B plus A bar C bar plus A bar C bar plus BC bar. Again you can see that there are two terms, that is the second and third term is repeating two times. Now we will come to the next example. Realize the Boolean function F is equal to bracket start, again the bracket start, A B bar C bracket close dot, again bracket A dot B bracket B bar bracket close with the whole bar, fine, plus BC the whole bar using basic logic gates. Realize the above function F after minimization. That means there are two parts of this question. First you implement it without any minimization and then again you implement the same function after minimization. So what you have seen that without going for the Boolean minimization, we can see that we require 3 input AND gate. 3 input AND gate, how much you require? You require one number. Then you have got 2 input AND gate, how much you require? You got 3 numbers. You require 2 input OR gate, you require one number, and NOT gate you require 2 numbers. That means you see that you require OR gates, you require NOT gates, and you require AND gates having different input. The same Boolean expression after minimization, we will see how many gates are required. After going for the Boolean reduction, you have seen that how many AND gates you require? You require only 3 AND gates, and all the 3 AND gates have 2 inputs, and you require one OR gate having 3 input. The important thing is that the minimization of Boolean function using algebraic manipulation and Boolean laws depend on the ability of the designer to apply Boolean laws and algebraic rules effectively. Now we will go for the minimization of Boolean function using the K-map, or known as Carnot's map. The Carnot's map provides a systematic procedure for minimization of Boolean function. The map is a graph of squares, each square representing a mean term or max term of the Boolean function. For an n variable Boolean function, the possible combinations of mean terms or max terms is 2 raised to n, where n is the number of variables, and therefore the number of squares which you have in the K-map will be 2 raised to n. The complexity of the K-map increases with the increase in the number of variables in the Boolean function, and the K-map is best suited for variables up to a maximum of 5. Now, use of K-map. How to use the K-map for minimization? So the rules for minimization of standard sum of product or SOP Boolean function using K-map. So step 1. For the given Boolean function, first prepare the truth table for the given 2 raised to n combination. The second step is draw the K-map having 2 raised to n squares, or we also call it as cells. The third step is place binary digit 1 in the squares or cells whose mean term produces an output 1 as observed in the truth table. The fourth step is look for adjacent squares, or we call it as cells, having 1 and combine them to eliminate the variable which differs in its value while moving from one cell to another. So what is the note we have to keep in mind? 2 adjacent squares having 1 eliminates one variable. 4 adjacent squares having 1 eliminate 2 variables. The adjacent squares having 1 that can be combined is of the order of 2 raised to n, that is 2, 4, 8, 16 as the variable size increases. Now we'll come to the rules for minimization of product of sum using K-map. Step 1. For the given Boolean function, first prepare the truth table for the given 2 raised to n combination. Draw the K-map having 2 raised to n squares or cells. Place binary digit 0 in the square cells whose max term produces an output 0 as observed in the truth table. The step 4 is to look for adjacent square cells having 0 and combine them to eliminate the variable which differs in its value while moving from one cell to another. Again the same note, 2 adjacent squares having 0 eliminates one variable. 4 adjacent squares having 0 eliminates 2 variables. The adjacent squares having 0 which can be combined should be of the order of 2 raised to n, that is 2, 4, 8, 16. This 16 comes when the number of variables in the function are 4, that is a, b, c and d, or as the variable size increases, the adjacent squares that can be combined also increases. Now we'll use the K-map. Now we'll realize the Boolean minimization using K-map. Let us have a function f is equal to a dot b plus a b bar c plus a bar b c bar plus bc bar. So we can see that this function, Boolean function, have got 3 variables. They are a, b and c, either in its complement form or in its normal form. Therefore, when we prepare the truth table, the number of possible combinations is 2 raised to 3. That means you will have got 8 rows of, or the 8 different possible combinations of the variable a, b and c. So let us prepare the truth table. Now we have prepared the truth table. We can see that the column 1 we have got the variable a, column 2 we have got the variable b, column 3 we have got the variable c, then a dot b, then one main term, the second main term is a dot b bar dot c, the third main term is a bar b c bar, the fourth main term is b c bar, and the final output function f, which is equal to a dot b plus a b bar c plus a bar b c bar plus b c bar. So you can see that the function f has an output equals to 1 for the mean terms of the 4th, 7th, 8th and 9th row. You can see that the 4th row, that means when a is equal to 0, b is equal to 1 and c is equal to 0, has its output value is equal to 1. Similarly, when a is equal to 1, b is equal to 0, c is equal to 1, has got the output value equals to 1. Similarly, when a is equal to 1, b is equal to 1, c is equal to 0, has got the output value equals to 1. And when all the variables, that is a equal to 1, b is equal to 1, c is equal to 1, has got the value equals to 1. Now the next step which you have to follow. Draw the K-map, because you have got 3 variables. So you will have 8 squares or cells. How you got 8 squares? That is 2 raised to n, where n is equal to 3, or 2 raised to 3, that is equal to 8. Fine. So we will make a Carnot map as shown. Now place binary digit 1 in the square whose mean term results in the Boolean function output equals to 1 as per the truth table. So you know that the mean terms for which the function f is equal to 1 are a bar b c bar, a b bar c, a b c bar and a b c. So now I put 1s in the squares whose function f is having a value equals to 1. Now the step 5 is combine the adjacent cells having 1 and remove the variables which differ in its value while moving from one cell to another. So I have combined the ones. You can see that using the circle as green and the other circle as yellow. If you see that the adjacent squares are combined using the rounded squares or circles colored as yellow. When you see that when I colored it as yellow, when you move it from the second column to the third column, that is the second column is B bar C and the third column is BC, and the second row that is named as A, you can see that the variable which is changing is only B. B is changing from B bar to B. C is remaining as C and A is remaining as A. So, we will remove B because only that variable is changing, therefore, we will write it as A dot C. Similarly, we take the two ones which is rounded up using the green square. You can see that BC bar is remaining as such and only the variable A is changing from A bar to A. Therefore, we will remove the variable A because it is changing from A bar to A, whereas the variable BC bar is remaining as such, therefore, it will be BC bar. So, therefore, after reduction the final function f will be equals to AC plus BC bar. Now, we will go for the reduction of the Boolean expression using K-map in POS form, where the function f is equal to, have used the same function f is equal to AB plus AB bar C plus A bar dot BC bar plus BC. So, again you have got three variables, therefore, the possible number of squares will be 2 raised to 3, that is 8, and first you prepare the truth table as we have done in the previous case. We have prepared the truth table and then we prepare the K-map. So, we have prepared the truth table. We can see that the max terms of second, third, fifth and sixth row have the output function f is equal to 0. You can see that the second row, the third row, then you come to the fifth row and the sixth row. You can see that the output value f is equal to 0. Now, we will prepare the Carnot map. Place boundary digit 0 in the square whose mean term results in the Boolean function output equals to 0 as per the truth table. So, we have put zeros in the K map for the mean terms whose function value f is equal to 0. So, you can see that I have put 0 for the mean term A bar, B bar, C bar. Then we have put for A, B bar, C bar. Then we have put the value 0 for A bar, B bar, C, and then we have put the value mean term value 0 for A bar, B, C. The corresponding max terms you can say it as, that is A bar, B bar, C bar, that is the mean term. The corresponding max term will be A plus B plus C. Similarly, for A bar, B bar, C, the corresponding max term will be A plus B plus C bar. Similarly, for A bar, B bar, A bar, B, C, that is the mean term, the corresponding max term will be A plus B bar plus C bar. Similarly, for the mean term A, B bar, C bar, the corresponding max term will be A bar plus B plus C. Now, as we had done in the previous case, combine the adjacent cells having 0 and remove the variable which differs in its value while moving from one cell to another. The adjacent cells are combined using the rounded squares colored as brown. You can see that I colored it as brown. That two zeros are combined because the combination should be in the form of 2, 4, 8, 16, 32 and so on. So, therefore, two zeros I have combined, there are adjacent zeros I have combined, and the variable that is changing is variable A. Only the variable which is same is B bar, C bar. So, I can write it as, that is in max term as B plus C. Similarly, the two zeros combined in violet, you can see that the variable which is changing is only the variable B. A bar and C as it is remaining constant. Therefore, we will remove the variable B, and finally, you have got A bar dot C, and in terms of max term we will write it as A plus C bar. The minimized Boolean expression in POS form f is equal to b plus c within bracket dot a plus c bar. Now we will come to the review questions. The first review question. The logic expression f is equal to a dot b plus b dot c bar plus ac is in which form? SOP form, POS form, standard SOP form or standard POS form. So we know that when a Boolean function, when it is in standard form, all the min terms or mass terms should have all the variables. So we have seen that you have got, it is a 3 variable function, but all the terms which are there, the min terms, all the 3 variables are not present. Therefore, we can say that this is in sum of product form, that is the option A. The number of cells in a 5 variable K map is, we know that for a m variable K map or an n variable K map, the number of cells or squares in a K map is 2 raised to n, that is where n is the number of variables. So we have got 5 variables, 2 raised to 5, that is 32, that is the correct option is B. Uniform propagation delay is provided by which type of logic? Hybrid logic, multi-level logic, 2-level logic and low-level logic. The correct option is C, because the propagation delay is uniform. Therefore, the 2-level logic has got uniform propagation delay, because there is only 2 levels, level 1 and level 2. The binary representation of the rows and columns of a K map are in EBCD code, which form? BCD code, XS3 code or gray code. The correct answer is option D, that it is in gray code. The simplification of a Boolean function having n variables, a group of 2m adjacent cell with ones leads to a term remaining with, there are 4 options: n minus m variables, m plus 1 variables, n minus 1 variables, n plus m variables. So we will solve it by using an example. Take an example. If n is equal to 3, we have drawn a K map having 3 variables and we have shown it some min terms having 0 and some min terms are having the output equals to 1. How many cells will be there? Because there are 3 variables, there will be 8. Suppose 2 adjacent cells have 1. Suppose I am just circled by that green, that 1 1. So how many cells you are combining? 2 cells you are combining. That means 2 raised to m, m is equal to 1. So therefore, how many variables are removed? You can see that the variable a is changing while going from the top row to the bottom row. BC bar is remaining as such. Therefore, you will remove the variable a and the remaining variables are BC. Therefore, after reduction, we can say that n, that is the number of variables, 3, and m is 1, 3 minus 1 is equal to 2. That means the remaining variables will be 2. Suppose I take the other example. If all the rows in the bottom are equal to 1, we can see that what is changing? The variable b and c is changing from b bar c bar to b bar c, then bc and bc bar. Only the variable a is remaining intact. So here how many cells you are combining? You are combining the 4 cells, or 2 raised to m, where m is 2, that is equal to 4. So therefore, if I write m is equal to 2 and we know that n is equal to 3, so 3 minus 2 is equal to 1. Therefore, the remaining variable is only 1, that is a. And suppose if all the 8 squares have a value equals to 1, then for how many squares are having equal to 1? All the 8. That is m is equal to 3, 2 raised to 3 is equal to 8. Therefore, n is equal to 3, m is equal to 3, 3 minus 3 is equal to 0. That means if all the 8 squares having equal to 1, then the function output f will be equals to 1. Each of the sum term in a standard SOP is called max term, min term, literal or prime implicant. The correct answer is option B, that is min term. We have got some practice problems as practice problem 3. We will be solving some of the problems in our next lecture. Thank you all. Keep practicing. Until then, see you all.